So a quick review. R greater than or equal to 0 denotes the set of non-negative real numbers. All real numbers bigger than or equal to 0. And a metric space is a set M along with a distance function d from M cross M to here. So between any 2 points in the metric space, there is a distance satisfying the following properties. The distance from x to x is always 0. The distance from x to y is greater than 0 when x is not equal to y. Distance function is symmetric. Distance from x to y is the same as the distance from y to x. And then you have this thing called the triangle inequality. Distance from x to y plus the distance from y to z is less than or equal to the distance from x to z. Now, the triangle inequality is called the triangle inequality because it, sort of brings this figure to mind. Not that we're talking about triangles. Okay, we're talking about a metric space, which is an abstract thing, and, what you think of as a triangle may not be a triangle. Like, for example, when the basic example of a metric space is just the real numbers itself, the real numbers itself is a metric space where the distance from x to y is just the absolute value of y minus x. So I'm not proving it's a metric space, but it is. Okay? And the triangle inequality holds here. Right? I mean, how does the triangle inequality look here? I mean, if you have x to y and y to z, it could be like this. X, y, and z could be here. Right? So here's d1, here's d2. Distance from x to y plus the distance from y to z is d1 plus d2. And the distance from x to z is d1 plus d2. So here they're equal. Whoa. Okay. So here they're equal. But it could be otherwise. Right? I mean, if z is inside here, distance from x to y plus the distance from y to z is what? What's the distance from x to y plus the distance from y to z in the case that I've drawn here?
B.
The distances are labeled here.
Equal to x to z plus 2z to y.
Which is equal to, in terms of d1 and d2.
Oh, I don't know how I missed d1 and d2 entirely. 1d1 and 2d2.
All right, and the distance from x to z is just d1. All right, so there's an example of the triangle inequality in action there. But there's no triangles in this metric space, not in any conventional sense. Right? There's no triangles here, but there's still a triangle inequality. Not that it has anything to do with triangles necessarily. It's just triangles are one thing that are a specific example of the triangle inequality. All right. So next. So a whole bunch of metric spaces on R cross R. So M is R cross R. So the two-dimensional plane, the XY plane, the same two-dimensional plane that you're used to from 7th grade onward here. Okay, and now when you're talking about the distance between 2 points in R cross R, a point in R cross R consists of a pair of points. So you never write this in this metric space. You never write that. It doesn't make sense. Unless X is a pair and Y means a pair, but probably not. The distance between 2 points here is like this. Points are pairs in this metric space. And, you know, the first metric space is, you know, this standard one. Right? The distance between these 2 points is the change in x squared plus the change in y squared square root, this Euclidean metric. Right? This Euclidean metric, you know, which satisfies this Pythagorean identity here. The distance between 2 points is just the length of a straight line between them. Right? So that's the standard metric in R cross R, although there's other ways to do it. This, you know, as the example I gave you before, I mean, if you're in a, you know, in a big city, you know, that's built on a grid, right? The streets are built on a grid. You don't measure the distance between 2 points as being along a straight line. You measure the distance in the number of blocks of travel it takes to get there. Right? I mean, assuming blocks are kind of the same size. Right? It's 2 blocks north, 1 block east. All right, and that's this metric. The distance between points x, y, and AB is this length plus this length. All right, it's the difference in the x absolute value plus the difference in the y absolute value. And that's called the taxicab metric. And then there's a third metric here in R cross R. We'll call it the max metric. It's actually got a different name, but we'll just call it that. So for 2 points x, y, and AB, the distance from x to y is just the larger of these two numbers here. The distance from x to a, right, or the distance from b to y. The absolute value of x minus a or the absolute value of b minus y. Whichever one is larger, that's considered to be the distance, and that's the max metric. So, like, here's an example of those 3 metrics in action here. I got these 2 points, 1, 2, and 4, negative 2. Right, in the Euclidean metric, right, so let's draw a triangle here. Alright, so this length is the difference in the x coordinates. So that's 3. Right, 4 minus 1 is 3. This distance right here is difference in the y coordinates. So it's minus 2 minus 2 is 4. And this distance right here is square root of 3 squared plus 4 squared, which is 5. Right, so the Euclidean metric gives you a distance of 5. And the taxicab metric gives you a distance of 7. And the max metric gives you a distance of 4. Notice the max metric is the smallest. The max metric is the smallest, and the taxicab metric is the biggest. So there's another, you know, these metrics are examples of the following. So if you have any p bigger than, it's p bigger than or equal to 1. If you have any p bigger than or equal to 1, then you can put a metric on R cross R that's defined like this. We're not going to use that, though. I mean, just, of course, we're talking here about p equal to 1, p equal to 2, and the max metric is actually the limit as p goes to infinity of this thing. Another example of metric space. This is a very nice one because it's used all the time, but you never talk about it in school. Um, by the way, if you're a math major, we do have a upper level course in geometry. There's no like set syllabus for it. So, um, depending on who teaches it, uh, it'll be completely different subject matter. Like somebody may be teaching non-Euclidean geometries, somebody better maybe teaching sort of more classical geometries. I mean, there's all kind of things which people might cover in there. But one of the things that might be covered would be like spherical geometry, or you could just go to there's a nice Wikipedia page on spherical geometry. Um, but I mean, just a brief discussion of it like this. Let M be the points on the surface of some sphere of fixed radius. For example, the Earth. I know the Earth isn't really a sphere. I mean, it's round. I know that's controversial to say it sometimes. Shouldn't be, but um, you know, assuming the standard model of the Earth that most people believe in, it's not exactly round. It sort of bulges out at the equator a little bit. But I mean, just as a rough approximation, it's something like the Earth. A great circle on a sphere is a circle that cuts it into two equal hemispheres. And of course, there's going to be infinitely many of these things. I mean, the equator on the Earth is a great circle, but you could slide the equator around, right? It doesn't have to be sort of that. I mean, the equator is the equator, but then you can take that circle of the equator, kind of slide it all over the sphere. The longitudinal lines on a sphere, right, the ones that go from North Pole to South Pole, those are great circles as well. So longitudinal lines in the equator, but there's plenty of others. And the cool thing about great circles is that any 2 points on the sphere have a unique great circle, which contains both of them. A unique great, not exactly, except if they're antipodal points. Any 2 non-antipodal points. You know what I mean by antipodal?
Oh, on the exact opposite side from each other?
Yeah, not the ends of a diameter. Any 2 non-antipodal points. Any 2 non-antipodal points on the sphere, like North Pole, South Pole. What do you call it? True north, true south, not magnetic north and magnetic south. Those are not quite antipodal, but true north, true south, those are antipodal points on the sphere. And those have infinitely, like all the longitudinal lines go through those points. But, the distance between them is always the same. Anyway, but any 2 non-antipodal points have a unique great circle which contains both of them, and that's the cool thing about it. So like with Dayton, right, Dayton, Ohio, is, directly north from what? I mean, it's not exactly directly. I mean, like, so what's that town? It's a little bit east of, I guess Cincinnati is like, so kind of like Cincinnati and Dayton are kind of on the same longitudinal line, I think, more or less. But there won't.
It's really something close to not.
Yeah, but there won't be any other great circle containing both. Not that Dayton and Cincinnati are points, of course, they're not. And the distance between 2 points is the length of the xy path along a great circle, the shorter of the 2 lengths. And that's a metric space. Now, there's an actual formula that goes along with that when you use these spherical coordinates. And that's something that can be covered in a geometry class. And then a final example. So this is no geometry whatsoever. Let M be the set of all f, such that f is a continuous function from 0 to 1 to the real numbers, from the interval 0 to 1 to the real numbers. For like example, any polynomial, p of x is in M, sine of x is in M, e to the x is in M. Rational functions like 1 over 1 plus x squared, where you don't have any vertical asymptotes inside, between 0 and 1, that's in M. So like 1 over x minus 2, that'll be in M. Right? It's not continuous everywhere, but the non-continuity is at 2, which is in this interval. So now you define the distance between two functions, f of x and g of x, as an integral from 0 to 1 to the absolute value of f minus g. That's a metric space. It's a really cool one, too. So they come in all shapes and sizes, is kind of what I'm trying to tell you. But we're kind of going to concentrate a lot on R cross R. All right. Definition. In a metric space M, and R bigger than 0, real number, positive, real number, R, define the open ball, given a metric space M, X in M, and positive R in R, the open ball around X with radius R is BRX, and it's equal to the set of all y in M such that distance from X to Y is less than R, strictly less than R. Okay, so everything that's got distance from X less than R. Is this round? I know I'm calling it the open ball, and I know I'm giving it a radius. Is it round? Is it somehow round? Is it somehow circular? Is it somehow spherical? For example, in this metric space here, set of all continuous functions on the interval from 0 to 1, and distance is the integral of the difference, absolute value of the difference of the two functions. Is the open ball around some center here going to be round? Guys? Who? How about with the taxicab metric? Is the open ball going to be round? Or the max metric? Will the open ball be round?
An element in M, would that be a set of points? Or
No,
would that be one
point. The metric space is just a set of points.
I would think it'd be round.
I mean, we're calling it round. We're calling it a ball and calling it the radius R, but it depends on the metric space. It doesn't necessarily have anything round. It doesn't have any shape at all. It's, it brings to mind the idea of roundness, but it doesn't have to be. It doesn't have to have any shape, period. It's just this thing called the open ball. So, for example, consider the metric space, which is just the real numbers, where the distance from x to y is just absolute value of x minus y. Here, the ball of radius r around x is the set of wall y, such that distance from x to y is less than r, which is equal to the set of wall y such that, well, what's the distance from x to y? It's just that. What's this? Set. What's this set here?
Would it just be a set of all points between x and y? Well, within the same distance as x and y?
We have to describe it in terms of r.
Oh, I don't know.
Would be all the points like within our distance of x.
Mm-hmm. Which would, what would be the upper and lower bounds here?
Like x plus r and x minus r.
Mm-hmm. Not including
Which
point.
Yeah.
So this is, actually, let me make it 2 dots first. So this is x plus r, this is x minus r, and then in the middle is x. All right, so it's this interval. All right, so this is the interval the open interval. Right, you know, which is also denoted x minus r comma x plus r, although this is not a great notation here because it's used for too many other things, right? So the open interval from x minus r to x plus r, is that round? No. It's a line. There's no roundness there, you know. But it's still a notion of a ball. Okay. Another example. And I think maybe I need a whole page for this. That's fine. So in R cross R, so the two-dimensional plane with Euclidean metric, distance from x, y to a, b being the, x minus, no, square root of x minus a squared plus y minus b squared. Okay, so in R cross R with the Euclidean metric, right, the ball of radius r around a point xy is, right, the set of all points AB such that the distance from xy to AB is less than r. Right, it's the set of all points, you know, whose straight line distance is less than r. Oops, put the square root thing there. X minus a squared plus y minus b squared less than r. All right, so what's that? So I mean, if here's the point x, y, you know, or if you want to write it a different way, so in a more sort of calculus-friendly format, that's what.
That would be a circle?
Yeah, centered at x, y, right?
Yeah.
Not the whole thing, not the boundary, right? Not including the boundary.
Not the boundary.
Yeah.
So
If
I'm
we
not
said
sure
less than or
right
equal to
now.
r, that would include the boundary. But the open ball does not include the boundary. All right, so that's the, you know, this standard. So this length of this here is r. I guess I didn't do a great job of that. Let me see. That's the circle. Here's the center. Maybe I should call it AB here. It's a set of all x, y. All right, and so this distance here is r. And so we're talking about everything inside this circle here. So that's the, you know, the standard sort of intuitive notion of open ball. Now, if when someone says open ball, you like to think about this, that's great, you know, because it's a nice intuition to work with. I think most people do. When they think about metric spaces abstractly, this is the first thing that comes to mind when, you know, trying to get an intuitive idea of what's being discussed. All right, so this is the.
If you're defining the function, like the open ball function at AB, wouldn't the center of the circle be at AB?
Right, yeah.
Sorry, just checking.
Yep. So it's all the x, y's inside here. Disk of radius r centered at AB, not including the boundary. In r cross r with the taxicab metric. Whoops. So is so in r cross r with the taxicab metric, what do we have?
Would that make a 4-point star?
Yeah, right. So it looks like this. So let's give it like an XY axis, but we'll center it at AB. Right, so the ball of radius r around AB is the set of all x, y such that x minus a plus y minus b is less than r. So here we have a plus r. Oops. See if I can do this. A plus r, b plus r, b minus r, b a minus r. So this is a plus r, a minus r, b plus r, b minus r. I don't think I quite got it right. And then all along this line here, the sum, yeah, it's not quite right. How can I get this drawing to work? Let me see. Close enough. So this is AB here in the middle. A plus R, A minus R, B plus R, B minus R. So in this case, the open ball is everything inside this diamond shape. Again, nothing round about this, but that's the open ball around AB that you get in the taxicab metric. Still a metric space, not as pretty as the Euclidean one, but you know, it's a metric space nonetheless. And then in R cross R with the max metric, what do you think you get there?
A plus symbol, positive symbol. Or at least the shape of one. Like it just two crossing lines.
Not quite a plus. Is the max of so the ball of radius r around AB, it's equal to the set of all x, y such that, right, the max of the difference in the coordinates x coordinates or y coordinates is less than r. So for example, if this is the point AB, right? I mean, you know, as you were just thinking, you know, like A plus R or B plus R would be up here. And B minus R is down here. So the distance between A, B and these points is R, right, in the max metric. Right, the distance from here to here in the max metric, the difference in the B coordinates is R. And the difference in the A coordinates is 0. Oh yeah, I guess I should. Right, so
yeah.
A plus R, B, A, B plus R, A minus R, B, A, B minus R. Alright, so this is A, comma, B plus R. So now, how far can I move that line? in the A direction. How far can I move that line in the A direction? Right, the difference in the x coordinate and the y coordinate, right, between a point on this line and the center is less than r. Right, but the difference in the a coordinate, right, has to be less than r as well. They both have to be less than r. But, you know, any one, is as long as they're both less than r, that's fine. Right, so that's another way to say it. It's the set of all x, y, such that x minus a is less than r and y minus b is less than r. Right, when you're talking about the max of these two being less than r, what you mean is that both of them are less than r. Don't matter which one is bigger, just both of them are less than r. So this is a plus rb, and this is a minus rb. So which other points do I have here? Think about moving that whole line, and what do I get? What do I get? I get this whole square. Right? This is the point out here, a plus r, b plus r. So any point inside of this, and that's not in the open ball. You know, these corner points are not in the open ball. Right? But anything inside this square is.
Okay. Makes sense.
Yeah. So it's this whole square. Right. If you're saying the distance, the distance of the max of a minus b, sorry, the max of a minus b, comma x minus y less than r, you mean that just both of them are less than r. Right? Because the bigger one is less than r and the smaller one is smaller than that. Or they're the same size. So it's just this whole thing here. So if you view all three together, so all three of these notions, so all three of these metrics on R cross R give different notions of BRAB. Right, together, so viewed together, it's as follows. So I will take this one. Here. So that's the open ball with the max metric. The open ball with the Euclidean metric is the circle that is inscribed in this square. Right? So it's this circle that touches not the corner points, but the these points here. So there's this ball. All right, that's the ball in the Euclidean metric. And the ball in the taxicab metric is this square inscribed inside the circle. All right, pretty cool. So as you can see, the taxicab metric is always the smaller of the three. The Euclidean metric is always at least as big as the taxicab metric. And the max metric is bigger than the other three. And they coincide at those four corners of the diamond there, of the diamond shape. Pretty neat. All right. Other metric spaces, I'm not gonna touch them. So now that we've got the notion of an open ball around us, we can talk about open sets. So definition: a set O. So if M is a metric space, M, a set, a subset O is called open when for each X in O, let's say A, for each A in O, I'll call it X, for each X in O, there is R bigger than 0, such that the ball of radius R around X is a subset of O. So intuitively, like using R cross R, we have kind of this idea. All right, this is O, and then for any X inside there, you know, there's some ball that you can. I need to fill it in. There's some ball around X that will land inside of here. Okay, so for example, the ball of radius R around X in any metric space is open. The open ball is open. Let us prove that the open ball around any X in a metric space is itself open. Oh, let me make that a homework problem. Let's make this a homework problem. I'm going to make that a homework problem. All right. So you're gonna want to be able to prove that itself there is an open set. It satisfies the definition of an open set. So what are some ways that we can sort of get some ideas how to work with that? Let O1, O2, O3, like that, all be open sets in a metric space. Yeah. So let's just say that we have a bunch of open sets in a metric space M. Okay, then the union of all those sets is still open. Proof. So we've got a bunch of open sets in a metric space M, and we want to show that the union of all those open sets is still open. Okay? What was the definition of an open set? The definition of an open set is, for each x in the set, there is R such that the ball of radius R around x stays inside the open set. So like the idea is here's O, this circle over here, and then for any x inside there, there's some radius small enough, that keeps you inside of O, or something like this here. So now I've got a bunch of open sets, and I'm going to take their union and ask if it's still open. Okay, so I have to prove for every x in the purported set that there's a ball around x that stays within the open set. So let x be in the union of those open sets. What does that mean? If x is in the union of these sets, O1, O2, O3, union, so on and so forth. What does it mean? What does it mean for x to be in the union of all these things?
It's in at least one of those.
Yeah. So therefore, x is an element of OI for some I. All right. Because OI is open, OI is an open set by assumption. Let me write it as an if then. If R. So because O1, because OI is an open set, what does it mean? What's the definition of open? Right here. It's open when there is what?
Some R greater than 0, so that the radius of R is still in the set O.
Yeah, the ball around X, the
Ball,
radius R is still in L. Because it's open, there is R bigger than 0, such that the ball of radius R around X is a subset of OY. Therefore, what? We need that the ball of radius R around X, is in the whole open set. Well,
O sub I should be a subset of that whole open set.
Therefore, B sub R of X is a subset of OI, which is a subset of all of this union. So that's a union of infinitely many sets, actually. As required. You don't even have to have it's a set of countably many open sets, a union of countably many open sets. It doesn't even have to be countable. It could be uncountable. But we're not going to worry about that. Oh, okay, 115. All right, so I'm going to have an assignment posted, right, in just a little while here. And if you need to talk to me on Tuesday or Wednesday, I'll be available. And I will have your exam graded. I'm still waiting for one person to take the exam. He had some problems, so he was not able to take it. So he's got to make up the exam still. So I can't quite hand it back till he's taken it. All right. So other than that, I'll see you on Monday. Okay. All right. Everybody have a great break.